Atoms consist of electrons zooming around a positively charged core known as the nucleus. During chemical reactions, it is these electrons that allow atoms to bond with other atoms, sometimes releasing energy in the process. A typical example of the release of this chemical energy is the combustion of gasoline inside your car's engine. The nucleus, however, is a much more potent source of energy. The nucleus consists of two subatomic particles, protons and neutrons. Protons are positively charged, while neutrons have no charge. The number of protons in a nucleus is known as the atomic number, and it dictates the type of element to which a particular atom belongs. The mass number, or nucleon number, of an atom is the sum of the protons and neutrons in its nucleus. Atoms of the same element always have the same number of protons, but may possess different numbers of neutrons. These are known as isotopes of the element, and some of these isotopes provide an opportunity for energy extraction. Isotopes of heavy elements, such as uranium-235, can be broken down into lighter elements, for example, barium and krypton, in a process known as nuclear fission. Let us look at a particular example of this reaction. In a fission power plant, the reactor core consists of uranium-235 fuel rods submerged in water. When a neutron is fired at one of these rods, it penetrates a uranium-235 nucleus. This makes the nucleus unstable, causing it to split into lighter nuclei called fission fragments and releasing energy in the process. If you compare the total mass of all the byproducts to that of the original nucleus, you will find that there is an imbalance. The byproducts actually have less mass compared to the uranium-235 nucleus, and this difference in mass is called a mass defect. This discrepancy occurs because mass and energy are two sides of the same coin, and thus some of the mass is converted directly into energy in the form of kinetic energy and radiation. The exact amount of energy released can be calculated using Einstein's mass-energy relation, E equals mc squared, where m is the mass defect and c is the speed of light. The reaction also releases other neutrons, which then go ahead and penetrate other uranium nuclei, creating a chain reaction and causing a vast amount of thermal energy to be released. All this energy causes the fuel rods to heat up the surrounding water, changing it into steam, which can then be used to generate electricity. This chain reaction can quickly get out of hand, so boron control rods are introduced into the core to control the reaction by absorbing some of the neutrons, thus reducing the number of fission reactions occurring per unit time. This controls the power output and prevents overheating of the core itself. A neutron moderator such as graphite is used to slow down fast neutrons into slower ones called thermal neutrons. Thermal neutrons are desirable because they are much more likely to cause nuclear fission, thus propagating the reaction. Lastly, the byproducts of nuclear fission are radioactive and thus have to be disposed of with proper care. That's it for how nuclear fission works. If you enjoyed the video, please leave a comment, like and subscribe for more content.